Hello, my name is Michael Simpson. Now, I've been working in the composting field for over 30 years. And presently, I'm now a professor of resource management at Antioch University, New England. And I do have the great pleasure to be presenting this webinar, providing some basic guidance for the siting and operating a municipal scale composting facility. But first, let me tell you all the good work that the Northeast Resource Recovery Association does for this region. NRRA is pleased to let you know that this webinar is made possible due to a grant they won from the United States Department of Agriculture's Rural Development Program. Under this program, this particular initiative is to train municipal operators and school officials on how to work together within a community to address a shared challenge, such as the recovery of materials from being disposed at a landfill. And it's because of the USDA that this particular online training is free to you. So we would ask, after you view the webinars, to please complete the webinar evaluation. This helps NRRA to better understand what steps to take to better assist you and your community with managing materials comprehensively. Now, once you submit the evaluation, you can then download a certificate of completion for this webinar. And this webinar is just the latest in a series of operator trainings offered by NRRA, all of which you can receive professional development or continuing education credits. Now, for myself, I have personally been associated with the Northeast Resource Recovery Association since its inception. But at the time of its inception, it was known as the New Hampshire Resource Recovery Association. Now, over the decades, I have observed the evolution of this organization to what you see today, and the incredible dedication of the NRRA staff to expand the level of service, education, and technical support to its member communities. Now, this is the current reach of the organization, but many of you may not know that over the decades, the organization has often been called upon from other parts of the country to provide insights into why this cooperative market model has been so successful over the decades. One of NRRA's great successes is its School Club initiative. Through this initiative, NRRA is doing its part, helping to train the future decision makers that will be taking on the new challenges of managing materials and energy. But they will do it in a way that is environmentally safe, economically sound, and sustainable over the long run. And it's through this effort that staff has developed curriculum and tools that school administrators and teachers can use. And if so requested, NRRA staff can arrive on site to provide direct technical assistance. And as many of you are aware, NRRA strives to keep you informed, not only with its monthly newsletter, but from the staff touching base with you periodically by phone or even visiting your site, all the way up to the more formal meetings that are held throughout the year. And we must not forget that NRRA prides itself in bringing its whole community together at their annual conference. This is always a great opportunity so that municipal officials can share lessons learned with each other. And it's an opportunity to hear from well-respected professionals in the field to discuss the dynamics of materials management and recovery from the local to the global scale. So let's now get down to business with this webinar. What I will be covering today are considerations that a community needs to understand if they're going to separate and aerobically compost the organic fraction of their waste stream. The specific topics to be introduced today will how to maintain a healthy compost pile, It's actually a biological system, and you have to pay attention to that. What to consider when choosing the most appropriate location for the composting operation. I do want to focus on designing the compost pad so it can perform throughout the year, and develop the right mixture going into the system. We call that creating the compost recipe. And then I'll cover the process or the compost methodology itself and the alternatives one can use in order to degrade the organic matter down to a safe product that can be put on the land. And obviously, once you have the compost, you're going to need to move it off site. So how should you look at marketing and end users? I want to close with focusing specifically on food waste due to the landfill bans that are starting to pop up around the country. But first, let's just get down some basic definitions. Aerobic composting. From a solid waste manager's point of view, it is a managed process that needs to be paid attention to so that the organisms in the composting pile get what they need. And in this case, it's aerobic, which means they need oxygen in order for them to decompose in an efficient manner. Now, the finished product, compost, resembles a soil, but it's actually a soil conditioner. But we're going to talk about how to produce it so it can be safely handled and stored, and that end users will be happy with the product. Now, the organic fraction of the waste stream can be significant. And if we exclude paper, which is organic, it still could be as high as 70% of the residential waste stream. Now, currently in the US, large-scale facilities that take in organics range from yard trimmings or yard waste and grass being the largest number of facilities, but in part this is because 25 states in the country have landfill bans not allowing this material to be disposed. Of the 5,700 facilities approximately, 4% or 225 do take in food waste already, but they mix that with yard waste also. Now, the most basic understanding of a composting process that will ensure that it's sustainable is that you need to realize that it is an ecosystem with a whole set of living organisms that evolves and changes over the period of the composting process. Now, these organisms are like us. They take in oxygen, they give off moisture and carbon dioxide. And if you put them in a pile, the respiration activity, the living activity of these organisms will also release heat, and the pile will insulate the heat and it will start to get hot. If you're composting correctly, the temperatures in the center parts of these piles should be getting up between 130 and 140 degrees Fahrenheit. This is termed the thermophilic biologic range, okay? And the organisms that can live at these high temperatures are called thermophiles. Now, this high temperature is actually an advantage for a number of reasons in a composting operation. One, the organisms that live at these high temperatures are specialized and quickly break down the substances like cellulose, which are hard to break down complex organic molecules. Also, these high temperatures will kill pathogenic organisms so that the final product is safe to handle. It also kills weed seeds, and you really do not want this in your final compost product. And it will control vectors such as insects and flies, because the high temperatures with mixing will kill all the eggs and any pupa that may be forming. Some of the organisms that are in this biological film that is inside the compost pile are fungi, many types of bacteria, and then there's Actinomycetes. It has characteristics both of fungi and bacteria, but it's actually a life form in a class unto itself. Now, all these organisms optimally like oxygen, and they do their best job in an oxygen-rich environment, but they also need moisture because they actually live in the water film that surrounds the composting particles, and that's how they decompose them. So now let's get down to some practical considerations. First, how does one find an appropriate location for a composting operation? Now, this image reflects an analysis of multiple possible locations for a food waste composting operation in the area of Amherst, Massachusetts. Each blue circle represents a possible site. Now, to narrow this list down to what we consider the final choices, we use something called exclusionary criteria. Some of these criteria are referencing regulatory siting requirements, such as required distance from surface or groundwater. But also, some reflect actually context and where the development is in relationship to valued natural resources or other developed areas next door. The exclusionary criteria creates a short list, and then we move to a second round of criteria called preferential criteria. These criteria are developed in collaboration with a community based on the preferences. And I want to focus on one of these specifically, and we'll be addressing this throughout the composting presentation. And that is the criteria of the potential of odor impact. All composting facilities create odor. Okay, so they're a point source of odor that is dispersed by the wind over distance. So usually you're interested in where the prevailing winds are going and taking the odor. But just because composting facilities create odor, the question is, will they have impacts? And that really depends on how close sensitive receptors are. Because over time, as the wind blows, the odors are diluted. So what do I mean by a sensitive receptor? Well, this may be a neighbor, such as a school, a daycare facility, a hospital, a retirement community. Or it could be even a community park that is loved by many and there's many people that come to it. Or it could be a high density residential area. So mapping out where you potentially would have such impacts is important in order to create a short list of possible sites for composting. So now let's turn to choosing the proper composting method for a specific site. Generally, all composting methods have some permutation of 4 steps. There's an initial mixing step where the recipe is created. There's the active composting process, which comes in many forms. There's a finishing step, what we call a curing step, that allows the compost to be at the point it can be applied to land. And then there's usually also a post-processing step. And this is really driven by the specifications of who's going to use the compost and what they're looking for in a final product. Now, in the mixing step, one of the earlier challenges is balancing moisture and oxygen. As I said, those microorganisms need both. And so to really understand this, let's get down to the particle size. Now, these are organic particles, and around each particle there's a biological water film, and it's inside those films that those organisms actually like to live. And they actually decompose the organic particles on the surface. So the more surface area, the faster the decomposition. But at this level, you also need enough porosity or pore space between the organic particles to allow for good air circulation. The reason being is these microorganisms are in there and they need to get oxygen to them quickly. So you need a combination of this biological water film and the proper porosity to allow aeration. Now, if a pile gets too dry, there will be no place for the microorganisms to live. And as a result, you'll see a slowing of the decomposition of these materials, and it will cease altogether if the pile gets really dry. Alternatively, if it gets too wet, it will diminish the ability for oxygen to circulate and get to the organisms, causing the whole system to shift from an aerobic or oxygen-rich to an anaerobic oxygen-poor environment. Now, anaerobic microorganisms, which can live in this low oxygen, unfortunately are not good decomposers. The decomposition process will significantly slow, and also some of these anaerobic organisms produce odors. So what is the right moisture content so that we get the right aeration? Well, generally you want something at around 50% by weight moisture. A good way to tell if you have 50% saturation is to grab some compost and squeeze it as hard as you can. And if a little drop of water forms at the bottom of your fist, it's around 50%. So that's a good field test. Now, you can be within a range around 40 to 65% and still have composting occur. 50% is where it's most optimal. But if it drops below 40%, it's going to slow because it's too dry and there's no biological film. If it gets above 65%, there's not enough porosity because all the pores are filled with water, and you'll move into anaerobic composting. It again will slow, but in this case, you'll get odors. Now, another challenge as you create the recipe to put in a composting pile is to make sure you get the right nutrient balance. Okay. And really, what we're looking at is two major nutrients. It's carbon and nitrogen. Now, the carbon provides the energy for the microorganisms to do the work. And so if you have enough carbon, they have enough food, and you're going to see good decomposition. But at the same time, they need enough nitrogen, which are the building blocks of life for these organisms. So they can grow, reproduce, and actually have large populations, so the decomposition rate is quite fast. So you need an ideal carbon-nitrogen ratio. And you can see, looking at this list, that it can vary quite a lot, you know, from something like wood, which is 700 parts carbon to 1 part nitrogen, okay, all the way down to something like food waste, okay, which is what you're seeing is 15 parts carbon to 1 part nitrogen. So what is the right ratio? Well, to do that is you bring in different types of organic waste and you mix them, so you try to get an ideal mix ratio. And that is, you want something around 25 parts carbon to 30 parts carbon to 1 part nitrogen. Okay. Now, if you get more carbon, if you get greater than 40 parts carbon to 1 part nitrogen, you have a lot of energy, but you don't have a lot of nitrogen in order for those organisms to reproduce and the populations to grow. So you'll have a slow composting process, and materials will have to be on site much longer. However, if you have something less than 20 parts carbon to 1 part nitrogen, you actually don't have enough carbon. It will be used up really quickly, and the piles will get hot. And as a result of the hot piles, the excess nitrogen will turn into nitrogen odor compounds, and you'll get odor release. And so you want to avoid being above 40 and below 20 parts carbon to nitrogen in order to have an efficient composting operation and to avoid odors. So once you get the materials mixed and in the piles, what is the right methodology for composting? Well, the choices you're going to be making is, how do you want to aerate that material? How do you want to ensure that oxygen stays in that material? And there's many ways of doing that. How do you want to continually mix the piles? Because, the question is, you want to make sure that you have hot temperatures touching all parts of the material at some time. Do you want to size reduce? Remember what I said is that decomposition by the microorganisms is a surface phenomena. So if you increase surface area by making smaller particles, it will speed up the composting process. Obviously, seasonal issues and changes in droughty and wet conditions, as well as hot and cold conditions, are important to consider, especially here in the Northeast. And then site constraints. Once you've chosen a site, you're limited, and you're going to only be able to accept so much material based on the composting method you choose during the year. And then previously, as I said, what is the context? Where is this facility located? And what do you need to do to make sure that there are no impacts emanating at the facility that's going to have impacts on your neighbors at some distance. And obviously cost is always a consideration, but it really is related to all the decisions above that you're going to make about the composting operation. Now, most people are familiar with this type of composting. It's called windrow composting. You put your materials in a long row and you use a piece of equipment to turn it. Most communities have something like a front-end loader. Operating a front-end loader with a windrow system is that it's important how you turn the piles so that not only are you releasing the carbon dioxide and the water vapor, the byproducts of aerobic respiration, but you're also getting oxygen into the pile, and you're mixing the pile so that everything is at some point at the center in a thermophilic range. Now, there are specialized turning equipment. Some are attachments, such as this Wildcat turner, and it can be pulled with anything with a PTO drive. What it does that the front end loader can't do is it size reduces and it increases surface area and thus allows the more rapid decomposition process. And then you can have actually self-drive turners, such as the Scarab at the bottom. And they do the exact same thing as like the Wildcat, but what's different about these is they can actually compost larger operations efficiently, and they have the capability of adding water to the pile as it's being turned in case you need to do that. Now, there are many what we call static aerated pile systems where you actually are only turning the pile maybe once, where you actually have two phases. You have a phase one static aerated pile, and then you flip it and have a phase two. You put these pads down that have pipes. They can just be plastic pipes and holes, and then you put the material over it, and these pipes are attached to a blower. So if you're going to have a static aerated pile system, you're going to have an electric source. And these blowers blow air through the pile, or they can suck air through the pile, depending on the time of the year. And often they're covered with something, either a geotextile, or there's now what's called a gore cover, which actually allows carbon dioxide and moisture to be released from the pile, but limits the amount of rainfall going into the pile. But most of them use a finished compost. They'll put about 2 feet of finished compost on top of the piles, and the compost basically insulates the pile, so the whole pile is now in a thermophilic range, in that high temperature range, and allows rapid decomposition. In-vessel systems often use a combination of both windrows and air. This is a facility that was built up in Hanover, New Hampshire. It had air coming up through the floors of these bays, and then it had an automatic turner that you put the material in the front end, and the turner would run down the pile and kick the material back. And so after about 21 days, the material that you put in the front end came out the back. And so you had the combination of a static aerated pile oxygenation system, and you had the turning and the size reduction that allowed rapid decomposition. Now, what's interesting about these systems is an in-vessel system, you actually can capture all of the emissions coming off that pile, which includes odors. And you can route this material through what we call a biofilter. It's another biological system where now we have bacteria in that system that are cleaning the odors out of the air. And so this is a really great alternative if your only site you have is right next to some sensitive receptors. Now, the appropriate sizing of a site, it really is driven by how do you start your decision making. One of the decisions is that you've chosen a site because that's all you've had, and that immediately drives how much material you can bring onto the site, how fast the thing decomposes with the methodology you choose, and how much storage capacity you have before you have to start to move materials off the site. So starting with the site limits, the material being accepted. Or you can make a decision that we need to serve a certain waste shed, and that determines how much material you're going to have to handle, and then you look for a site with a certain composting methodology in mind that is large enough to handle an annual amount of material coming on the site and getting the compost off the site. Now, as I said, many people don't have a choice. They may have very limited sites to choose from, and as a result, they often don't have the most ideal configuration for materials handling. This site is spread over 5 acres, and so you can imagine that moving materials from one stage to another, especially if you're doing it with front-end loaders, will take time. And so it will add to labor costs, it will add to operating costs because of the configuration, and you need to be aware of that. Now, ideally, what you want is a system like this where materials sort of run in a circular pattern, and you don't have a long linear serpentine site. And so materials going in circulate, and materials going out are pretty close to where things come in. And so you should think about how you site things so that you can minimize materials handling and operating cost. Now, once you have your site location configuration, what I really think you need to focus on first is where to put the composting pad and how to design it. Now, you need a composting pad that operates in all seasons of the year. And one of the major issues around a composting pad is that you need to avoid standing water. If you have water that is next to a composting pile, it will soak up that water like a sponge. And what it will do is the bottom of the pile will have all the pore spaces filled up with water so oxygen can't get into them. And so, as I mentioned earlier, you'll move from an aerobic set of organisms to an anaerobic oxygenless set of organisms. And as a result, the decomposition process will slow significantly and you'll get odors. And I will add that any puddles that are near a composting operation for a long time will also become an odor generating source every time a piece of equipment runs through it. So building the pad is really important to avoid future problems and doing it correctly. Now, there's some pretty simple rules of thumb. You basically want a pad that will support equipment year-round. You definitely want it to shed water away from the composting pile, so it should have a slope of 0.5% to about 1%, so the water can run through it. And then you want to make sure that you have the pile set up parallel to the fall line not across the fall line, so the water can run between the piles and not into the piles. You want to always avoid standing pools of water, so you need to have maintenance. And you want to make the pad out of something that is of a material that is not going to be a contaminant to the final end product. Now, it's just some very simple guidelines when dealing with the pad and the contour and the location. One is, it's good to raise the pad above the surrounding natural contours and allow the water to shed off the pad very quickly. Now, if there's any possibility of runoff entering the site from upslope, you should create either a dike or a ditch to divert, the runoff around the pad so that water doesn't run across the pad. And finally, do not site the pad in a location where there is seasonally high water, evidence of a wetland, or you have shallow to bedrock soils. If you do, you're going to run into future problems unless you raise the elevation on that location so the pad is significantly above those, what we call restrictions. And it should be at a minimum of 2 feet above the restrictions, but ideally 4 feet. Now, this is a well-designed pad. You can see there's some ponding of water, but this was taken during a very intense rainfall. And within 2 to 3 hours, there was no water on this pad. Now, over time, pads actually do get rutted. You do have low areas, so it's important for periodic maintenance to maintain the pad so that the water will not stand and cause anaerobic conditions in the pile. Now, one of the things we think about in managing the process is what is the throughput rate. Now, the throughput rate is the time the material remains on the site. That is, what is the time period from it entering the front of the facility and getting the final compost product off the back end. Now, the throughput rate is really driven by a number of things. One is at what rate is the material arriving, and because the rate of material arriving drives how fast you need to move materials through the process. Also, what is the length of the active composting and curing process, or the finishing step? And that's important, and that's driven by the specific methodology you choose. And finally, you ultimately have a site constraint. You have a certain amount of area on the composting location. And so you need to ensure that the throughput rate is reflective of the total area so you do not get a buildup of material and a backing up of the process on site, okay? And so one of the things is be cognizant of how materials come on site and what you're going to need to do in order to get them off the site. So the throughput consideration, probably the most major factor is choosing the appropriate composting methodology. And so if you have site constraints, you may have to be choosing a methodology that speeds up the decomposition process. If not, you're going to have to slow down acceptance of material at the site. And you're going to have to manage your materials during the composting process, such as combining materials as they decompose into larger piles so that you're freeing up space for new material to be built into new composting piles. So once you have the materials in your composting, the question is, when are we done with composting? When is it ready? How long do we have to compost? And the key to this is really monitoring, and the monitoring is using temperature. You can also use oxygen, but temperature is probably the best way to monitor the health of a compost pile. As I said, you sort of want to, in all parts of your pile, you want to have thermophilic, temperatures, okay? And so you need to continually monitor the piles. Now, if the pile temperatures are going down, it either be because you're done composting, but if it still looks like it's not soil, then you're not done. And the temperatures are going down. Well, it's going to go down for you don't have enough moisture, you have too much moisture, you didn't really make a good mix of material, and you may have to remix it. But using the temperature and recording that temperature so you can look at trends over time is important, especially if you have multiple windrows or multiple static aerated piles. They're going to be composting at different rates, and they're going to be in different stages of decomposition. So you need to monitor all those piles periodically. And you should be able to compost right through the winter if you design and operate the facility correctly. If you don't operate through the winter and you haven't planned on this as far as the size of your site, then what's going to happen is the throughput rate is going to be diminished because you've cooled down the piles. It's not composting at the aerobic stage of high temperatures. And as a result, materials may start to back up. Okay, and if you have site constraints, the size of the site may dictate that operators all of a sudden are scrambling to figure out how to deal with material on a site. And so they often will take shortcuts, make compromises because they're running out of room. But experience has shown time and time again that when such shortcuts are taken, it will eventually lead to closing of the facility. Now, this is either because regulators come in, because you've created a lot of impacts, both environmental or nuisance conditions, and they'll shutter you. Or you're creating a quality of finished product, and you got to get the finished product off the site, but it's not done. And so it will not be really marketable. Or you're increasing the cost of dealing with the material backing up, and those costs are much higher than whatever you budgeted for. Now, for a well-maintained composting process that occurs throughout the whole year, and that's assuming that you basically maintain good compost pile moisture, you're getting good aeration or oxygen throughout the whole composting process, and you actually create a good mix at the beginning of nutrients. And the pile temperature starts to cool because the material no longer looks like the organic material. It's now looking like a soil product. And it continues to drop. You've turned the pile or you've aerated the pile, and it still continues to drop. Well, you're getting towards the end of the composting process. Now, once its temperatures back down to ambient temperatures, that is, the temperatures of the surrounding atmosphere, you still need to let it rest. We call it the curing period or the finishing step. And this allows for the reinoculation of the finished soil product with organisms that are compatible with soils, what we call the mesophilic organisms. And so you need to allow it to cure, and we call this to allow it to stabilize or be stable. Now, if you move material off your site and give it to someone before it's stable, and they apply this unstable compost to their lands, what's going to happen is this compost still wants to finish breaking down. So it's going to rob nitrogen from the soil, and it's going to compete for the nitrogen that these plants that grow on the soil need. And so, plants will either be stunted or you'll be killing the plants. And this is especially true for seedlings. They cannot compete with the compost for nitrogen. Also, if the unstable compost is still high in what we call organic acids, and it can actually burn vegetation if you broadcast it onto it. And so it's important to have that curing step in your composting process, and you need to plan for that time of the material stabilizing. Now, when you get a finished product, the question is, who's the client? Now, the marketability of the compost, like recyclables, is determined by the specifications of a particular end user. But unlike a materials recovery facility, a MRF, that takes recyclables and prepares it for manufacture, where the manufacturer is the end user, the composting facility is both a materials processor and the manufacturer, and thus they're creating the final end product for consumption, either wholesale or retail. So once you've created a stable finished compost, you must find a home for it. Okay, you don't want it to start backing up and taking over area of the sites that you didn't plan on, and thus taking shortcuts to deal with lack of site capacity. Now, there are a number of marketing considerations that drive the post-processing step in the composting site, and the post-processing step is driven by market specification. But you can decide, well, do we create a bulk product that's lower grade for the larger bulk markets, such as land restoration, erosion control, landfill final cover, ball field construction. All these markets, they'll pay for the material, but they'll pay a relatively low price. But your post-processing costs are minimal in order to produce this product. Or you can make a decision that we're going to create a blended final product for very specific horticultural or agricultural markets. And they'll pay a high price for a good quality product, but the post-processing costs are also increased. Or does the facility do both? Whatever the choice is, it's inherently critical that the material is moved off the site in a timely manner so it doesn't back up. At a minimum, the post-processing is to ensure that the compost product looks like a soil product. That is, it doesn't have contaminants or visible contaminants in it. Well, one way to deal with this is to, at the front end of the facility, only accept certain types of material, and thus you can minimize your contaminants coming in. Alternatively, at the back end, you can screen out your materials and thus remove those things that end users would definitely not like to see in that final product. But such screening should also might want to make the material look more like soil. This is a finished compost product. It's stable, but it's sort of clumpy because it had a high percentage of leaves and yard waste in it. So if you have a certain market that's not looking for a mulch, but it's looking for something that looks like soil, you're going to need to basically create smaller particles from the larger particles. Well, one way is you can pound or pulverize it, and you can do that actually with the choice of the right screen, so that it basically can screen it. The other thing is you can actually just not have any kind of size reduction and just have it screened into two size particles. The fine particles are the ones that you would sell to the end user, let the end user take. And the larger particles would just be reintroduced into the composting process at the front end and would continually get smaller as it goes through the process a second time. And so really, we're looking for something like this. You know, whether it's a high-end horticultural or agricultural blend is really dependent on what they want as far as what else they want in that material, such as types of fertilizer and nutrient. Now, as I mentioned previously, and as I sort of stressed throughout this whole presentation, that odor generation, you know, is a major issue for management of a composting facility. And again, it is the major reason that facilities have closed historically. And so paying attention to a number of issues, but realizing odor generation is often a result of site constraints and shortcuts that managers take. And ultimately, what shuts down a composting facility is that they did not design the site correctly. They chose a too small site. They may have not chosen the right composting methodology to get the highest throughput rate. And as a result, they have high cost and they're getting very low revenues from a poor quality product, and thus all those facilities I mentioned that closed because of odor is ultimately because they just didn't have the financial resources to correct the problem. Now let me close by just turning to food waste. Now, food waste is sort of the last frontier for composting, and it's, again, it's a significant part of the waste stream. But and what we're seeing now, there is a trend developing, especially on the west and east coast of the U.S., where food waste is being banned from disposal in landfills. In our neck of the woods, the states of Vermont, Massachusetts, and Connecticut have already enacted legislation over the last 4 to 5 years with the intent to add food waste to their already current leaf and yard waste bans for disposal. And this is just an example. This is the summary of the legislative mandate for the state of Vermont for businesses, communities, and citizens. Now, as you see, it's been ramping up as far as generators, the size of generators that have been banned from disposal since 2014. But by 2020, no food waste will be allowed in landfills. From a compost operations point of view, what is clear is that when food waste is added to an already, let's say, leaf and yard waste municipal operation, the management, monitoring, and record keeping of that facility will need to step up to a new level. And there are a couple of other challenges that need to be considered. Now, this is just a waste sort that was done at a food waste generation site. This happened to be a convenience store. If you look, the package component of this food waste stream can be as much as 63% by weight from this business sector. And such waste streams coming into a composting facility will create major operational challenges and could diminish the quality of the end product. So the acceptance of food waste means you're going to be accepting the packaging along with the food waste, and there needs to be a way to deal with that either before the material gets to your facility or at the facility, either at the front end, at the back end, or both for the composting process. An additional challenge that is also has risen is that when you're bringing in food waste, you're bringing in a significant amount of high nitrogen material. And remember that carbon-nitrogen ratio? Well, you're going to have to find sources of additional carbon out there. Obviously, leaf and yard waste is a good source. Manure bedding, especially horse bedding is another good source, or, materials such as, wood chips that are, from a forestry operation. But except for the leaf and yard waste, the other materials are in high demand in other sectors of the economy. So the challenge is finding these materials at a low enough cost so it doesn't break the bank of the operation. So that's it. There'll probably be subsequent trainings with more specifics about operations, management, record keeping, monitoring, and marketing of the compost. But for now, we're done, and I want to thank you for taking your valuable time to sort of build your knowledge about the steps to site and operate a composting operation in a non-impacting manner. And please remember to complete the webinar evaluation so that NRRA can better assist you in providing you the technical assistance and continuing education to handle your materials. And again, once you submit the evaluation, you can download the certificate of completion that you can use for your professional development. Now, thank you and have a great day.